In our previous video, we have used the Hess law that teaches how we can combine the enthalpies of reactions that we know so that we obtain the enthalpy change of our target reaction. In our case, we were saying, well, if you know the change in enthalpy from A to B, and then from B to C, and then from C to D, you can combine those to obtain the change from A to D. However, if for whatever reason if you miss one of these from B to C, say, then it's hard to combine the reaction to obtain your target reaction. So chemists came up with a standard state, something that we're going to call the roof. So we're going to measure the energy or the enthalpy change of all our substances that it takes to go to the roof. What does that mean? Well, it means that if we know this distance in energy, again, and we know this distance, I don't need any other intermediates as long as I have both to the roof. So if I know that I'm just 2 floors away from the roof and I am 5 floors away from the roof, I need to flip one so that roof and roof goes away. Hopefully you're following the metaphor, and you still obtain the same result. So what is this roof that we're talking about? What is this absolute reference point in chemistry that we are talking about, that all chemists one day got together and after having some tea they agreed that that would be our standard state, our roof. The standard state is our roof. So what is the standard state? The standard state, and I'm just reading here, is the state of a material at a defined set of conditions: pure gas, solid or liquid in its most stable form, and usually temperature 25 Celsius. If it's a solution, 1 molar. That's our roof. So let me give you an example. If I need to send water to the roof or to the standard state, it says pure gas or pure solid. So we're going to send all these elements to their standard state. So for 1 mole is oxygen and oxygen. Notice that hydrogen and oxygen are in form of H2 and O2 at room temperature. So you will not see atomic hydrogen, it has to be molecular hydrogen. This would be, if you will, the reaction that allow us to connect the roof, again, the standard state and our molecule. Okay, so one has to practice a little bit to be able to understand how any molecule has the reaction between the formation of that molecule and its elements. That reaction specifically is called standard enthalpy of formation. So if it's formation, it means that for the case of water is hydrogen in here, and we will have to specify if it's liquid, but these two are definitely solid. So what is the standard heat of formation? It's a reaction that comes from the roof to that specific molecule. The standard state, I will repeat, is the elements in their most stable form. So at room temperature, hydrogen is a gas and it's in form of H2, and this is something that you need to know from your previous courses in chemistry, and oxygen is also a gas. The enthalpy associated to this reaction, we call that enthalpy of formation. Okay, so it will be very important to practice, for example, write the enthalpy of formation of ammonia. There will be always one here, and nitrogen is N2 because that's the stable form at room temperature and it's gas, and you'll have 3/2 of hydrogen gas. This is the heat of formation, in this case if it's gas, the heat of formation of ammonia. Okay, let's practice a little bit to understand how we can apply this standard state, this roof, this reference point to practical questions in chemistry. Just another slide to just emphasize what we have said. Now the change in enthalpy for any reaction, when going from reactants to products, the change will be the heat of formation in which this our roof, if you will, of the standard state will be the heat of formation of products minus the heat of formation of reactants. And that's easy to do because any molecule can be tabulated into its heat of formation. So let's again, now we're going to do the application. Imagine that we want to calculate what is the enthalpy change of this reaction. And why are we even interested in knowing that? Well, we may want to know how much heat or how much energy you can get out of burning acetylene. So that's actually a very useful combustion. You reach very high temperatures. So we want to know, using heats of formation, enthalpies of formation, we want to know the enthalpy change of this reaction. First of all, we're going to write the formation reactions for each and every one of these compounds. First of all, acetylene, if it's gas, notice that it has to be gas here, it comes from its elements in their most stable form at room temperature. Carbon at room temperature is a solid and it's in form of graphite, like the one you have in your pencil. Hydrogen is H2 and it's gas. And you go to the tables and you will find heats of formation of all possible molecules, and this is the value of the heat of formation of acetylene. The heat of formation of carbon dioxide gas, again, is from its elements carbon and oxygen. And finally, the heat of formation of water. Notice that we did not include the heat of formation of oxygen because oxygen is already, if you will, on the roof. It's already in its standard state. It's O2 gas. So the heat of formation of oxygen, we can safely say that is 0. So now that we have all these energies that connect the roof with, I will keep using this metaphor, hopefully it's useful, the standard state of the elements with the molecules, let's see if we can combine these reactions to finally find the change in enthalpy of this reaction. So let's arrange them. We want acetylene on the left. So notice that then we have to, by the way, we want 2 acetylenes, so we need to multiply by 2 our heat of formation and change the sign. Remember here that this was positive because acetylene is on the right. Now in here, if it has to be on the left, you have to change the sign, and if you want 2 acetylenes, you need to multiply by 2. Now, we want 4 CO2s. 4 CO2s the CO2 is already on the right, however, we want 4 of them. Okay, and finally, we want 2 waters, so we need to multiply the heat of formation of water by 2. Oxygen, hopefully, it will show up, if you will, magically. Let's see. 4 carbons and 4 carbons disappear because they're on both sides of the arrow. The hydrogens also disappear, and what we get as a result, notice that yes, oxygen showed up, not magically, actually we were very much aware that they would show up. We obtain the overall. So when we combine all these enthalpies, we can find the enthalpy change of this specific reaction. And this is because we came up with a standard state with this roof so that it magically cancels out. Again, it's not magic, it's, again, we just decided that the standard state would be the elements. So of course, if you have a carbon on the left and a carbon on the right, they will show up as carbon solid on the left and on the right. Okay. There is a formula if you don't want to spend or waste, if you will, a lot of time cancel out things. The formula is, well, you just take the enthalpy of formation of products minus the enthalpy of formation of reactants multiplying by the coefficients. So in this case, the enthalpy of formation, the enthalpy change for this, if we apply the equation, this equation that you see here, it would be 4 times the enthalpy of formation of CO2 plus, now 2 times the enthalpy of formation of water, and now negative the enthalpy, negative 2, because we have a 2 here, so 2 times the enthalpy of formation of C2H2, and you would say, well, and now 5 times the enthalpy of formation of oxygen. But notice that this is 0, so we don't even need to include it. This equation here is the same that we did up here. So yes, you don't need to write all the equations. You may safely apply this simplified equation.